Welcome everyone to Avantier's webinar, where we'll dive into the fascinating world of microscope objective lenses. These are critical components in microscopy imaging systems, allowing researchers to observe fine specimen details. Whether you're new to microscopy or looking to expand your knowledge, this video will cover essential details about microscope objective lenses, their key features, and their role in scientific research. Let's get started. Let's begin by understanding what microscope objective lenses are and why they're so important. Objective lenses are vital optical components in microscopes, designed to provide detailed and precise observation of specimens. Manufacturers offer a variety of designs tailored to specific applications: high-power lenses for detailed observation, low-power lenses for broader views, oil immersion lenses for high-resolution imaging, long working distance lenses examining samples through thick glass walls. Many objective lenses include advanced construction features, such as spring-loaded retractable nose cones, to protect both the lens and the specimen from damage. In addition, long working distance objectives offer a large space between the lens and the sample, making them ideal for imaging fragile specimens or working with samples housed in specialized chambers. Infinity-corrected objectives provide flexibility by allowing compatibility with various microscopy accessories such as filters, polarizers, and beam splitters, further expanding their applications in advanced imaging techniques. Now let's talk about some key specifications imprinted on objective lenses. These details help researchers select the right lens for their experiments. Look for numerical aperture, NA, defines light gathering ability and resolution. Magnification determines the number of times the image is magnified. Optical tube length ensures compatibility with the microscope setup. Aberration correction improve image quality for clearer observation. These markings, often found on the lens barrel, help users better understand the lens capabilities and ensure optimal performance when paired with the ocular lens. Let's take a step back and look at microscopes as a whole. Microscopes are optical devices designed to magnify objects, revealing details invisible to the naked eye. They project images to the eye, a camera, or a video device. Modern microscopes are complex devices composed of lenses, filters, polarizers, beam splitters, imaging sensors, and illumination. Proper illumination ensures clear images, and techniques like Kohler illumination optimize lighting by providing uniform brightness while preventing the direct imaging of light sources like filaments. Speaking of illumination, let's explore 3 common methods. 1. Bright field illumination backlights the sample for clear observation of structural details. Most effective for specimens with opacity variations. Less suitable for highly transparent objects. 2. Dark field illumination directs light obliquely, making the sample appear bright against a dark background, enhancing contrast. Ideal for observing transparent or unstained specimens that lack sufficient contrast in bright field illumination. 3. Epi-illumination directs light from above the objective lens, making it ideal for fluorescence microscopy. Compact design simplifies setup while providing precise illumination intensity control. Each method serves a specific imaging purpose. The appropriate technique must be chosen based on the specimen type and desired contrast. Today, we've covered the fundamentals of microscope, from the key specifications of a microscope objective lens to advanced illumination techniques. Both objective lens and illumination setup play critical roles in a microscopy imaging system for providing high-quality magnified images that are essential for powered optics for scientific research and groundbreaking discoveries across various fields. Thank you for joining us.
See you in the next webinar. Avantier, empowering optical innovations.